Okay, so welcome back everybody. I'm going to go ahead and review some key concepts from chapter 12. Now keep in mind, I'm going to briefly go over some of these concepts because I do review the examples or examples that better explain what's going on in other videos. Make sure you're still reading chapter 12 to understand what's going on. If you haven't read chapter 12, it might be a little difficult following along. But let's go ahead and get started. So now we're moving on to more complex designs, right, in chapter 12. So before we had designs that had one independent variable. So just to give you an example of what that might look like, we had designs that had one independent variable. And here you have one example of what that might look like. And keep in mind, the dv, I'm assuming you know that, right, at this point, that there's always a dv. So you have an independent variable, you have a dependent variable. In this example, we have cell phone use as an independent variable, which is either you don't have it or you do have it, right? You do have a cell phone or you don't have a cell phone. Now, keep in mind that throughout I might switch to calling this independent variable distraction, but for now let's call it cell phone use. One independent variable, two levels, right? And the dependent variable is reaction time. So that's what we've had so far. But now in this chapter, we've added a second independent variable, right? We have designs that have two IVs and one DV. So here you have the same example, but we've added another IV. The IV we've added is age, right? So now we in addition to looking at distraction or cell phone use, we have the age of the driver. Are they older or younger? The DV is reaction time. Keep in mind that sometimes the DV is reaction time, especially in the examples in your textbook. Keep in mind that they switch it to number of accidents for some of the studies because they looked at both. So reaction time is how long the drivers take to brake, right? So if you're driving, you notice someone runs in front of your car, how long does it take you to stop the car, right? So keep that in mind. That's what we're talking about. We had the previous examples with one IV, two levels, and the new examples with two IVs, one DV, right? And two levels per IV. Keep in mind, this new design, it's new to what we're covering in lecture in the chapters, but actually it's not new to you, right? You've done this kind of design in lab, right? You have at least two IVs and you have one DV. And also keep in mind, in everyday language, we think of understanding the world this way. We don't think about, well, how does gender impact how you do? How does stress impact how you do? How does the opportunities you have had in life impact how well you do in college, right? It's not just one thing we think about. We think about all these things. Well, how did gender impact opportunities? How did coming up in a wealthy family and neighborhood impact the quality of the teachers and the quality of opportunities? We think about problems and understanding the world in this way. Now we're thinking about what does that look like in a study design when you have more than one IV. One thing you're going to notice though is that it does get more complex in terms of what you have to do to make it a study as soon as you start adding IVs. So here you have one IV, right? If you put this in a table, this is what it looks like. Distraction or cell phone use, on cell phone or not on cell phone, one level or the other. That's the study design. If you recruited participants for the study, you only have to worry about those two conditions: on cell phone, not on cell phone. Remember, this is the only situation when you have one IV, this is the only situation where the number of levels is equal to the number of conditions. But now we have two IVs we're dealing with. As soon as you add that second IV, now you've doubled the conditions, right? We have older and younger in addition to distraction, right? The distraction type, on cell phone or not on cell phone. So now we have to worry about 4 conditions, and if we want equal number of participants in each condition, think about what that means. Let's say I told you I want you to recruit 30 participants per condition. You just had to recruit 30 participants, but let's say it was per condition. Well, in the first design, 1 IV, that's 60 participants. You add that second IV, now you have to recruit 30 times 4, 120. Then you'll see what happens when you add a third IV. Then you double this, right? So now you have 8 conditions, and you'll see that visually in the next few slides. But keep that in mind. As you start adding IVs, the requirements to do that study start doubling. Sometimes they exponentially increase, right? So it's more work the more IVs you have. There's more to keep track of. Here you have an example of what that would look like visually. So we're going to go over what main effects are really quickly. Let's see if I cover that in the next slide. No. So I want to remind you all what a main effect is. A main effect is when you're just looking at 1 IV. So for example, here I have the first study design I gave you with 1 IV. If I'm looking for a main effect of being on a cell phone, I'm asking, is there a significant difference between how long people take to break? Remember the DV is breaking onset. Between how long people take to break when they're on a cell phone versus not on a cell phone. I'm just looking at 1 IV, and I'm looking at the levels within that IV to see if there's a difference between the levels. That's a main effect. I'm actually going to go back a little bit. Let's see if they pop up again. There you go. Okay. So in that more complicated design where you have a 2x2, I kind of hesitated because I haven't reviewed that with you yet, but a 2x2 is when you have 2 IVs and each of the IVs have 2 levels. So when you have a 2x2 design like you have here on the right, you have 2 IVs to consider. So you're checking for 2 main effects, right? You're checking it for a main effect for distraction, on cell phone, not on cell phone, and for age, younger compared to older. So keep that in mind. We're checking for how many main effects there are in some problems, and there can be no more than 2 main effects when you have 2 IVs. In other words, the number of main effects or possible main effects is equal to the number of IVs you have in that study design. If you have 2 IVs, at most you can have 2 main effects. If you have 3 IVs, at most you can have 3 main effects. If you have 10 IVs, at most you can have 10 main effects. Now, even though you might have 2 IVs, you can have 2 main effects, but you can also have 0 or 1. So let's go over this example so you can kind of get an idea of what I'm talking about. So in this design, let me look at the DV. So the DV is number of accidents, and you're looking at younger and older drivers, and you're looking at distraction, right? Were they on the cell phone or not on the cell phone? So when you're checking for a main effect, and I've given you this kind of table, and you see this kind of information, let me actually go out of full screen. I want you to remember, ignore the 7s on the side for now. These numbers here, you see here, on cell phone younger drivers, that's the mean for all participants that were in that condition. So on average, younger drivers who were on a cell phone were in 10 accidents. On average, here, I'm looking here, younger drivers who were not on a cell phone were in 4 accidents. On average, older drivers on a cell phone were in 4 accidents. And on average, older drivers not on a cell phone were in 10 accidents. So keep in mind, these are averages for all the participants in that condition. You might have had 30 participants in that condition, and on average, they were in 10 accidents. So keep that in mind. That's what those numbers mean. Okay, now you see the 7s on the side? Those are the marginal means. So if I gave you this table, I wouldn't give you the marginal means. And if I asked you, okay, is there a main effect for age of the driver? I'm asking you, is there a significant difference between the younger and the older drivers? That's what I'm asking. What you need to do first is calculate the marginal means. Now, let me go out of full screen again. Let me remove some of the stuff here. There you go. So what you need to do, if I'm asking you about the age of the drivers, the age IV, you need to calculate a new mean just for age, right? Just for younger drivers, just for older drivers. And you want to get rid of, you see how on top here we have the distraction? That kind of breaks up the averages across the groups, right? You have younger drivers on cell phone, not on cell phone. Older drivers on cell phone, not on phone. But you want an average for all drivers regardless of the distraction, just breaking them up in terms of age, right? So what you're going to do, if you're looking at the main effect for these levels, for this variable, independent variable, you're going to average a new marginal mean, that's what this number is called, for younger drivers. So you look at younger drivers, and you're going to average any situation that has younger drivers, this one and this one, right? Younger drivers on cell phone, younger drivers not on cell phone. Those both have younger drivers. And you get a 7. 10 plus 4 gives you 14 divided by 2. Now, keep in mind, you're averaging. Initially, I would have said, well, you just average this way. You add these going this way, and then you divide by 2, right? From going from left to right, you add them and divide by 2. That is correct, but I want you to keep in mind that you're calculating an average or a mean, because later on when we add 3 IVs, that shortcut's not going to work. But you can use that for now, right? Okay, younger drivers, it's over here. I'm going to average this way, that gives me a 7. Older drivers is over here. I'm going to average this way, it gives me a 7. We have 2 7s. So what you're going to do is you're going to compare the marginal means, and if they're exactly the same, there's no main effect. If they're different in any way, even if it's 0.1, so I'm not going to give you a problem where there's that small of a difference, but I'm just saying, even if there is a small difference like that, I want you to report a main effect. And that's because I think it's unfair to ask you to assess whether it's a large or a small difference when the scale might, you have to know what the scale means. You have to know what the scale being used to measure those numbers mean, because a large difference is going to vary based on the scale you're using. If we're talking about, is there a significant difference between how much time people took to finish a race course, and I'm using milliseconds? Well, what is a big difference is going to change if I'm using milliseconds or if I reported it in hours, right? So kind of a tangent, kind of not, but the main point is if they're the same, then there is no main effect. If they are different, report a main effect. And look at essentially what you're doing. Now you have an average for younger drivers, ignoring whether they were on a cell phone or not. And now you have an average for number of accidents for older drivers, ignoring the distraction. So you're comparing overall, was there a difference between younger and older drivers? And then here, if I ask you for a main effect for the distraction, right, whether they were on a cell phone or not, I'm asking you overall, is there a difference in terms of the number of accidents for people who are on a cell phone and people who are not on a cell phone? That's essentially what I'm asking you when I'm asking for a main effect. And in this case, because the IVs are up here, you would go down. I said IVs, the levels for the IV are up here. You would go down, or think of it this way. You're looking for any condition where participants were on a cell phone, here and here, and getting an average. 10 plus 4, 14, divided by how many numbers you had? 2. Now here, every condition that had people not on a cell phone, you're adding those up and dividing by how many numbers? 7. Now, these numbers are going to vary. Keep that in mind. It just kind of worked out that way in this example, that you have the same number across all marginal means. Again, just to emphasize, if the marginal means are the same when checking for a main effect, there is no main effect for that independent variable. If the marginal means are different in any magnitude of difference, then you would report a main effect. Okay, so here you have some examples, and here they're showing you how they averaged, right? They were looking at a study where they were looking at how seeing different types of pictures impacted reaction time, and you really don't need to know what the study was about to work out this type of problem that you see here. So yes, in the exam, I'm going to give you some descriptions for some of the studies, not all. Sometimes I'll just give you a table like this. But when I do, read it, see if it helps. Sometimes it's helpful to understand the context of the study. But if I asked you here on this table, is there a main effect for word type? Nice, you have the reaction time is dV, but you really don't need to know that here. What you need to know is, well, okay, I'm looking at word type. The levels are aggressive, neutral. Let me work out the marginal means for aggressive and for neutral, right? So an overall mean just for aggressive, just for neutral. Here they're showing you the arrows to show you what they added and then divided. And you get 555 for aggressive and 557 for neutral. Now, in this kind of example, they would say, well, take into account whether that's a big difference or not. But in this class, at least for your exam, if there's a difference at all, even this small of a difference, you report a main effect. Now, in your textbook, they tell you the right thing to do, right? You should take into account, well, is that a big difference or is that not a big difference? So in the real world, do take that into account. Okay, is this a big difference considering we're looking at milliseconds? Probably not. But just to simplify it for you all, if you see any difference at all, report a main effect. Any differences I show you are not going to be this small. And this is how you would work out the marginal, well, the main effect for phototype. Instead, you see that they're going down, and they work out an average just for alcohol and a new average just for plant-based photos. And you see that there's even a smaller difference than the previous one. Now, especially here, in the textbook, they're going to tell you it doesn't look like there's a main effect because it's a difference of like point something. In any examples I give you though, if you see a difference, report a main effect. You see me saying that over and over again, right? That's usually because this is important. But also keep in mind, if you're in the real world, well then take into account the scale you're measuring in. If you're using milliseconds, and you see something like this, and they give you averages and you're comparing two different groups and you're doing this for your job, then take the scale into account. Okay, well, if it's a 0.5 difference, but we're talking about milliseconds, that's not much of a difference, right? But just keep in mind, last time I'll say this, probably not, that if there's any difference in the marginal means, report a main effect. Okay. So now we're moving on to interactions. Interactions, now we're looking at not just one IV, we're looking at how both IVs are related to the DV. Okay, so in an interaction, we're asking, does one independent variable moderate the impact of the other independent variable on the dependent variable? I know that's confusing, but hopefully in the next few slides, you'll have, the visualizations will help you follow along. Conceptually, it is important to understand what's going on, but you can get through some of the math problems at least without conceptually understanding exactly what an interaction is, but hopefully you do get it, right? So here you have this question that relies on you understanding an interaction. You've all asked questions like this. When we think in the real world, when we discuss topics, not even academic topics, we're often taking into account interactions. So here's an example that requires you to understand an interaction. does the effect of cell phones use on accidents depend on age? Right? Well, I'm fine because I'm younger. I don't get distracted when I'm on a cell phone and driving. You know, if you hear anybody say that, like, yeah, maybe for older people that matters, but not for me, you're talking about an interaction. So in your textbook, they discuss interactions in terms of the difference in the differences. I don't find that as helpful to help me understand what an interaction is. I think it's more helpful to think about moderation. Does the impact of caffeine on anxiety depend on gender? Or in other words, maybe there is I almost use interaction. Maybe there is a relationship or causal relationship between caffeine and anxiety, but maybe it's stronger for men than for women, or for younger people than for older people, right? That impact of caffeine on anxiety, right? That's an interaction, right? We're saying, does this relationship between this IV and this DV, does it depend on this other variable? Does it change when you introduce a second IV? Or another way to better think of it is, can we better understand the impact of this IV on the DV when we have this other this other IV? So, okay, let me say that again. So, can we better understand the relationship between this IV and this DV, so caffeine and anxiety, when we understand how this other IV moderates that relationship? In other words, when we understand how the sex of the participant, I said gender earlier, meant sex, but when we understand how caffeine impacts people of different sexual, of different sexes, right? That would give us a better idea of the impact of caffeine on anxiety for humans if we knew that, right? So keep that in mind when we're asking, well, yeah, but does it depend on socioeconomic status? Does it depend on gender? Does it depend on sexuality, right? I said that weird. Sexuality. Does it depend on gender identity? Does it depend on ethnicity? Does it depend on how privileged you were growing up? I was going to say that's an anxiety. That's an interaction. So here you have a verbal description of what interaction might be. The effect of one independent variable depends on the levels of another independent variable. Here you have a diagram that shows you what that might look like, right? So here you have anxiety as a DV. You have caffeine level, caffeine or decaf, normal cup of coffee or decaf coffee as one IV, 2 levels. And the other IV is the sex of the participant, male, female. Male represented by the blue line, green represents female participants. And if you look at this, look at caffeine. So it looks like, in terms of anxiety levels for people who drink caffeine, it does look like there's a sex difference, with female participants being higher in terms of their anxiety than male participants. But without caffeine, anxiety levels are similar. So here you would say, yes, it seems like if there was a significant relationship, you would say, yes, it looks like there is a significant relationship between drinking caffeine and anxiety, but it really depends on the sex of the individual. Because here you see that there's a higher impact for women. It looks like they both might be higher than the decaf condition, but it has more of an impact on female participants, right? So that's what an interaction is, right? It sounds less complex when I'm actually saying it. When we're trying to describe what's going on in an abstract way, it is a bit confusing. So here's another example. So here in this example, we're looking at the age of the participant, and we're looking in this case at gender, boy, girl, and we're seeing, well, does age or gender, does that relate to minutes youth are spending on phones, right? Now let's say let's say our main interest was like, well, is there a difference between how much time boys and girls are using their phones, right? Let's say that was our main question. Then you might say, well, there might be, but here when we add that second IV, age, well, let's look at it now, right? So at 5 years of age, there doesn't seem to be a difference based on this diagram, right? You see how the green and the blue line are both intersecting at that one point? Now look at 8 years of age. So it looks like at 8 years of age, you actually do have a difference. So is there a gender difference in terms of how often boys and girls use their cell phone? Yes, but it depends on age. It looks like earlier at 5 years of age, there's no gender difference. At 8 years of age, there is a gender difference. Now, keep in mind that there might be other factors that might be influencing this, right? So at 5 years of age, they're probably not going to have a cell phone. Even at 8 years of age, having a cell phone, that's pretty early on, right? So yes, there might be explanations for it, but that's what we're trying to understand, right? Here's another way to represent that same data. The main point I'm trying to show you here is that these dots, let me actually bring out the cursor again. These dots here are averages, right? So here's an average, here's an average, here's an average, here's an average. This is just how they choose to draw this. It almost looks like a correlation, but it's not at all a correlation. So let me go to that next slide so you can see. You can draw that same diagram in this way. And you see here they're the same, here they're different, right? At 5 years of age, they're the same. At 8 years of age, there's a difference. Now, it's the same diagram. Well, it's the same information, a different way of drawing that same information. You are going to see these type of diagrams because that's what your textbook shows you. But hopefully, this helps you understand what's being represented in those diagrams, right? I actually like this way of graphing this out better. So if it helps you, I would redraw this in this way, and maybe you'll be better able to visually see what's going on, right? Okay, well, it looks like at 5 years of age, there's no difference between boys and girls, but at 8 years of age, we do see a difference. That's an interaction. Okay, so this is not, I think the other examples, even though they seem more complicated, I think this example, they were trying to break it down for you, make it simpler. I actually think this one's more difficult to understand. So if this example doesn't work, skip it, okay? If you've been understanding what I've been talking about in terms of interactions up to this point, this example is not necessary, but let me go over this example to see if it helps, okay? It's not a bad example, it's more of like a representation of a study findings. If you were to do this kind of just for fun. Okay, let's stop talking about it and review it. Okay, so here you have two IVs. You have the type of food, ice cream or pancakes, and you have the temperature of the food, hot or cold. The DV is how much do people like the food. You're giving people this food. Some people are getting cold ice cream. Some people are getting hot ice cream. Some people are getting cold pancakes. Some people are getting hot pancakes. Then you're asking them, how much did you like this meal? Okay, you could kind of see, well, why would anybody want hot ice cream? That's weird. They're probably not going to like that. That's kind of the point. So you look at this diagram on the bottom right, and you see on the bottom, they have the type of food, right? So that's kind of where you have to keep track of the information. Where is one IV? Where's the other IV? One IV is always represented on the bottom. Here you have type of food. And the other IV is always represented by the color of the line. In this case, green is cold. Orange, I think that's, yeah, it's orange, is hot, right? So keep that in mind. Look and see where are they putting the different IV levels. Is it along the bottom or is it the color of the line? Okay, so let's look at just hot, actually, no, let's look at ice cream. Okay, so did the participants like the ice cream? It depends. It depends on whether the food was hot or cold, or the ice cream was hot or cold. If it was hot, they did not like it. You see how that orange point is pretty low? Whereas if the ice cream was cold, they really liked it. Okay, did the participants like the pancakes? It depends. If it was cold, you see that green line? It's low. If it was cold, they didn't like it. But if it was hot, they did like the pancakes. So did the participants like the food? It depends on whether it was hot or cold. They liked the ice cream when it was cold. They liked the pancakes when it was hot. This is an interaction. It's a funny example to me, but hopefully that helps you understand how this works, right? The relationship between the IV type of food and the DV liking it depends on whether it was hot or cold. You could also say that differently. Let me use the other IV, the heat of the food, right? The temperature of the food. Was the temperature of the food related to the participants liking the food? Yes. The temperature of the food was related to the participants liking the food, but it depended on what food they had, right? If they had pancakes, they wanted it hot. They liked it hot. They disliked it cold. If they had ice cream, they liked it cold, disliked it hot. So that's essentially what we're trying to show you here, right? There's this moderation going on between the IV and the DV and that second independent variable. But hopefully that last example where I rephrased it in a different way shows you that you can rephrase it in a different way where it comes out that one IV or the other is moderating the relationship. I would say go with what makes the most sense. For me, that first example makes most sense. The relationship between the type of food and whether people liked it depends on the heat of the food or the temperature of the food. Okay, so here you have another example. And in this example, we're looking at how often, so you're training your dog, and you're trying to see, is my dog learning? Is my training effective? When I'm working with my dog, does my dog sit and obey my commands? Your IVs are, I say nothing or I say sit, right? Like you could consider that a measure of, like, if I say sit, do all these dogs sit? Or if I say nothing, do they sit anyways, right? It's kind of the control group. Again, this is another, not as bad as the ice cream example, but it's a conceptual example. Okay, so either I'm saying nothing or saying sit, or I'm holding a treat or not holding anything. Okay, so does my dog obey me, right? Does my dog obey my sit command, for example? So what I say would be my IV, and the DV would be the dog sitting. Well, it depends on what I'm holding, right? If I say nothing and I'm not holding a treat, dog is sitting, like the proportion of times the dog sits, the number of times the dog sits is very low. Makes sense. I'm not saying anything, I don't have a treat. But if I say sit, then you see that the dog sits more often when I have a treat than when I have nothing. So there is an interaction going on. When I say nothing, give me a second. Whether the dog sits based on me saying sit depends on whether I'm holding a treat or not, right? In terms of visually seeing if there's an interaction, look at the diagram. If they cross like this, if they cross like that, if they look like they're going to cross, I'm not voguing, I swear. If they look like they're going to cross at some point, then it's an interaction. If it's completely parallel, right? That last one wasn't parallel. That one, that. If it's completely parallel, then there is no interaction. Okay? So keep that in mind. Parallel lines mean no interaction. Not parallel lines mean an interaction. So if it helps you think of it that way, that's a fine way to think about it, because they don't have to intersect, right? If they're not parallel, that's still an interaction. Okay. One thing I also want to show you is that you can flip how you're graphing this data on, let me see which one I showed you before. Okay, so the one on the left is the one you just viewed, right? Say what I say is on the bottom, and the color of the lines represents whether I'm holding a treat or not. But if I took that same data and put holding a treat or not on the bottom, you're going to get the same type of interaction. That doesn't change the diagram you get. That doesn't change whether you get an interaction. So hopefully this shows you that you can graph it either way, and that's still useful information you can use. So if I gave you a table, I'm going to actually go way back, like this, and you kind of got confused. Maybe you were like, oh, is that right? I'm not sure, when trying to work out the math on an interaction, which I haven't showed you yet, but I'll show you in a second. You can go here, you can draw it out, and if they look like they're going to intersect, then you can say there's an interaction. So you can always do that check. You can check and see, if I draw it out, are they parallel or are they not? Now, just so you know the types of interactions, if it's going from a large difference to a small difference, that's a spreading interaction. If they cross, it would be a crossover interaction. Okay, so this is the last thing I'm going to review on this video, looking for interactions based on the tables I showed you earlier, right? So if you had a table with 2 IVs and 2 levels each, this is what you would do to work out an interaction. For both the main effects and interactions, go to the other videos I use a tablet for, the iPad, to work out the examples by hand. I think those videos are more helpful in terms of understanding how to do the math part. I'm focusing here more on the conceptual part, so keep that in mind. Go look at those videos. Okay, one thing I do also want to mention, to look for an interaction, you need to have at least 2 IVs. If I ask you to look for an interaction and you have 1 IV, that doesn't make sense. I should never be asking you that. So if you get a question like that, automatically you should know that's a trick question. There's no way you could answer that with 1 IV. If I gave you 1 IV with 2 levels and I asked you is there a main effect, that question actually is valid. So just keep that in mind. You need 2 IVs to look for an interaction. Now, what you're going to do here is you're going to subtract. You have to choose the direction that you want to subtract in, and it's going to say go down. Always go down, but keep in mind, if you want to, you could always go left to right, right to left, from down up. Doesn't matter, but just to keep it simple, let's always divide down. Okay, so in this case, right, you don't really care about the IV names even. You just look at the cells, you choose a direction. I'm recommending go down, and you're going to go 551 minus 562. Here you have, in this example, they tell you it's a negative 11, and then on the right, we're subtracting down again. 559 minus 552 gives you a 7. Are those different numbers? If they're different in any way, say yes, there is an interaction. If they're the same, no. Let me actually go back. So essentially, when you're subtracting, what you're doing is you're subtracting here, this point, from this point. So let's say we subtract here, let's say there was a tiny difference, a difference of 2. And you subtracted this from this, that's going to be a larger difference, right? So you have two different numbers, you say an interaction. Here, that's exactly what you're doing, but you're looking at the means on a table. 551 minus 562, that would be that first point. Well, let me see, 551 minus 562. It's probably more like a crossover interaction. You don't need to know that part, but you could actually draw it out like I mentioned earlier and see it visually. All you need to know is if you subtract down and you see a difference in these numbers you subtracted, then you have an interaction. And I think it is helpful to know that those differences, those numbers, represent the points on this kind of diagram. If you were to draw it out, it actually would probably look a little bit more like this, not as extreme as perfect as that X, but oftentimes, probably all times, if you have a negative and a positive number, you're going to have some level of crossover. So, okay. Stop going on tangents, Professor. You might be thinking, that's not a tangent. That's good for you to know. But okay, all you need to know, if you have this table, subtract going down, and if those numbers are different, then you say there's an interaction. That's what you report. Likely there is one. If you have a negative and a positive, those are still different numbers. So if you had a negative 7 and a positive 7 after subtracting, so you do have to keep track of the signs. So if you had a negative and a positive 7, that's still a difference. Okay, so keep that in mind. For interactions, if you have a difference in signs, you would still say there's an interaction. Okay. Whew. Okay, so I'm kind of, you know what, let's power through this. Let's get through this. I'm getting a little bit tired because I've been talking for a while. I know you're tired. If you need to take a break now, take a break. But let's get through this, right? Because I think it'll be good to get through these slides. This part is pretty quick. It's about factorial notation, factorial design. Factorial design is pretty much when you have more than one IV. That's factorial design, right? So if you only had on cell phone, not on cell phone, if I only had distraction for my IV, that's not factorial design. But as soon as I add the age of the drivers, now I have factorial design. The main thing I want you to take away in this video, at least regarding factorial design, is factorial notation. In studies, you'll often find we did a 2x2, we use a 2x2 within subject's design. What does that 2x2 mean, right? So that 2x2 means that you had two IVs with two levels each. So here I have a blank times blank, right? Or blank by blank. You might have 2x2, 3x4. Now, it sounds like I'm listing out woodcuts, but I'm not. But these represent the number of IVs and the levels. It doesn't tell you anything about the DV. It tells you about the design of the study in regards to the IV and the levels for each IV. So when you have this, the first thing I want you to pay attention to is, well, how many numbers are there? Okay, so if I had a 2x2, how many numbers? 1, 2. 2. So you have two IVs. Each number represents an IV. So here I have those blank by blank. If you had two numbers, regardless of the value of that number, the minimum we know from knowing that there was a blank by blank, we don't know the numbers yet. The minimum we know is that there's two IVs because there's two numbers. Okay, just to say that again. To determine the IVs, look at how many numbers there are. Don't look at the value. If there's a 3x4, you don't care that it's 3. You don't care that it's 4. You care that there's two separate numbers. And that, the number of numbers, is how many IVs you have in that study design. Levels, that's the actual number, like the number value of that number, right? So if you have 2, that means you have 2 levels. If you have 3, that means you have 3 levels. If you have 5, that means you have 5 levels for that IV. So just to give you an example, that first one, 2 by 2 by 2, means you have 3 IVs, right? You have a 2, you have a 2, and you have another 2. So you have 3 IVs, and each IV has 2 levels. Second example, 3 by 3 by 3. That means you have 3 IVs, and each IV has 3 levels. That third example, 2 by 10, you have 2 IVs, right? You have a 2 and you have a 10, right? 2 numbers, 2 separate numbers, and one IV has 2 levels, one IV has 10 levels. Meaning, for example, the first one might be age, younger, older. Then maybe then the 10 might be something like how much experience you've had driving, right? I can't make up the categories right now, but let's say it's like, okay, you've driven for a year, you've driven from 3 to 5 years, you've driven up from 6 to 10 years, and so on, right? Until you had 10 different categories or 10 different levels. That last one, kind of just messing around. This, you would never see this in study design. Well, I don't want to say never, but you'd have to have a huge, immensely huge sample. I can't imagine a situation where you would want to look at all of this at the same time, but let's go through it just so you could kind of drill in this message of what this means. You have 3 numbers. 33 is one, 2 is the second one, 702 is a third number. We have 3 IVs. How many levels does each IV have? The first one has 33 levels, that second one has 2 levels, and that last one has 702 levels. That's kind of where it's crazy. That probably wouldn't ever happen. And a quick way to figure out how many conditions you have, well, you can draw this out, right? Or you can just multiply it out. Let's do that first one. 2 by 2, okay, that's 4. By 2, 8. That study has 8 conditions. Okay, let's do that second one. 3 by 3, 9, times 3, 27. We have 27 conditions. 27 conditions that you need participants in. That's already crazy. It was crazy with 2 by 2 by 2, but you do see that study design. But you see, as you add more complexity, the requirements to do that study, it's going to take you forever to do some of these studies. That last one, 2 by 10, right? 2 times 10, 20 conditions. I'm not going to do that last one. You can figure that one out on your own, but you can see that's going to be a huge amount of conditions you're going to have to recruit participants to participate in. But keep that in mind. This is what this means. That's how you figure out how many IVs from this information. That's how you figure out how many levels. And from this information alone, you can figure out how many conditions were in that study. You don't even need to know what the levels were, what the IVs were called, but you can tell just from looking at that first one or any of these, how many IVs, how many levels, and how many conditions. So be able to figure all of that out based on this alone. Okay, so I'm going to go ahead and stop there. In the next video, I'll review different types of factorial designs.